Okay. Gabriel from SAS would like to say something.
Hi, everybody. I'm just here to let you know that we'll be holding our first exam review for Calc 3 in Durland, over in the engineering building in Durland 1107 on this coming Tuesday, September 14th. We'll just be going over, actually, I think it's the exam I took in this class a couple of years back. Austin will be there as well, and we're just going to hold a quick review from 7 to 9. So I hope to see you all there. I hope to see a lot of you there, and good luck with studying.
Thanks, Gabriel. All right. Yeah, great. Okay. I will send an announcement later today with SAS review to the class, and I'll also send an announcement. We'll have a class review as well on Wednesday evening, and from 5:30 to 6:30. It's just going to be on Zoom, so I will record it and post it. It takes a few minutes after, so maybe check in around 7:30 if you weren't able to make it. I like for these reviews, what it helps me a lot with these reviews is to have questions ahead of time for people to send them to me, email them to me. And that way I can prepare a little bit and go over things that might help you the most. So there's that to pay a little attention to. I will also send a little more information drawing people's attentions to which room they should go to. This is already on the syllabus. If you go to the syllabus and look, you should be able to find where you're going for your exams. But I'll send an announcement this week. If you're with the Student Access Center and you've had a letter sent to me, you'll have some information sent to you also this week about how we're structuring those exams. Okay. Also, there just was posted on Canvas, you look under modules of this week, or I think it's actually posted for next week because that's the week of the exam. I posted a practice exam, a written practice exam. There'll be a online practice exam that you can take for extra credit over the next week. The written practice exam is the one I want to say is better to study from because I'm the one who writes the exam. The one online, some of those problems are written by me and other people, but a lot of them are just from the community. But the exam itself, the written exam, practice exam, is going to be a lot like, not exactly like, but a lot like the one that I'll write and that you'll have. There are also solutions to that written exam posted in a separate file. I suggest you take the practice exam before you look at the solutions. And one word of warning on that is that, I oftentimes will cobble together old exams. And so sometimes there's some errors on these solutions. If that is the case, please send me an email. I'll make the correction and try to get it corrected. Okay. That said, today, what I want to do is to go over sort of the last bit of material that will be on the exam, and that's vector valued functions. Well, maybe what the book calls vector valued functions. So this is section 3.1. Okay. What you may have noticed thus far in this class, and I don't know, maybe you're happy or sad about it, is it's a calculus class, and we haven't talked at all about any derivatives or integrals yet, which is a little strange. We just talked a lot about vectors and dot products and things like that. There's a reason for that. The reason is that calculus really does involve linearizing certain nonlinear functions. And so when we're in many variables, before we can talk about that linearization, we need to know a little bit of the linear algebra. So we've spent a little time on that. But right now, we're going to start talking a little bit about nonlinear functions. And there's a general type of function, which I would call a vector valued function. And I think the community, mathematical community and applications would also need. And that is just, it's a function usually on some domain, D, we'll call it D is our domain. And the domain is contained in some n-dimensional space. So the way you denote n dimensions is you write Rn. And R here stands for the real numbers. But yeah, so we have some domain, you can think of it some kind of big blob in, if you want 3-dimensional space or 2-dimensional space. And it takes values in an m-dimensional vector space. So these are vectors with m components. This is the general definition. Okay. And the way you would write such a thing is maybe, again, you're going to take n inputs and you're going to get m outputs, and you can label a scalar valued function for each of the components. And I'm writing this down because in applications, I think this is going to be, you're going to want to be able to work with things like this. However, this is a vector valued function. However, when the book talks about vector valued functions, the book talks about the case of n equaling 1. I'm not sure why, but that's what this book does. So they look at, and maybe it's because we're coming from calculus 1, right? So we're used to functions only of one variable, one independent parameter. However, again, we're in multivariable calculus. We will be getting to functions that involve more than one variable fairly soon. But right now, we're going to stay with one variable. So that when the book talks about vector valued functions, it talks about functions that look like this. They have a single parameter coming in. And these guys live inside, so a vector in R2 or R3. These are maybe there's a few questions where they go to like higher dimensions, but normally this is the setup. Now our vector valued function has a domain. So, and usually it's going to be a closed or open interval. So the way I'll write that often is like this, takes in the interval, a closed interval AB, and puts them into 2 vectors, or it could give you a 3 vector. And the way you want to think about this is you want to think about sort of the terminal point of that vector and of tracing out a curve in, say, 3-dimensional or 2-dimensional space. Of course, you can expand this. You can write this in one of 2 ways. In the online homeworks, they very much seem to have a preference for the standard representation using the basis vectors. So they will often write things like this, where you have some scalar valued functions and you multiply your standard vectors by them. But I generally will usually just put them into the vector. It's the same thing, it's just different notation. But just so you're aware, this will be the same kind of thing. Okay, so what I want to do now is I want to talk about some examples that we should start to feel comfortable with in this course. We will have need, as I said, there's this general definition that we want to understand exists that we probably will, we will start working with later in the course. But that's not to take away from the fact that the case of n equaling 1 is also very important, and we'll use that throughout the course as well. So there are some examples we want to get comfortable with, even in this one-dimensional domain case. The first is one that we've already dealt with, which is vector parametrization of a line. So, and there we just took, our interval was just the entire real line, our domain, if you will, is our entire real line. So I would just say it's equal to R. And the function had this general form, as we all know now. It looks something like, we take an initial vector wherever we're starting, and we multiply, or we add t times a velocity vector. And if you want to write it out in terms of something that looks like this, you can do so. You just have this type of form. Okay, so this is very familiar, hopefully. But we know how to do other things. So this is linear, and we've spent some time with linear. We also spent a little time with nonlinear things, and when we talked about quadrics. And one of those quadrics, or conic sections, as it were, that we want to be able to deal with would be like vector parametrization of an ellipse. So let's take a standard ellipse. So we'll give in other words, we'll give ourselves a sort of centered at the origin, sort of with the minor and major axes on the X and Y axes, or vice versa. So this would be a standard equation. You can always take any ellipse, rotate it, and translate it so it's of this form. So let's say we want to parametrize such a thing. Who has suggestions? Yeah. Sine and cosine? Sine and cosine are very appealing, right? I mean, they come to mind because we know how to parametrize a unit circle, or even a circle in general, right? We can use our cosine t, sine t, say. However, this is not a unit circle. So maybe if A equals B equals R, then we do get a circle of radius R, and we can parametrize it by just taking R cosine theta, t, R sine t. That's fine. Maybe I should use capital R since I got two R's here. Sorry about that. So what if, okay, so that's a circle, that's familiar. What if they're not equal? Anybody else? Guess? Very good, right. We can actually just take, let's assume, yeah, I mean, we can put A in front of it. It's fine just to actually do, so more generally, we can just do what was just suggested. We can just take R of t equal to A cosine of t, B sine of t. If you check and you put A cosine of t in for x and B sine of t in for y, well, the squaring will cancel the A and the B out. So you'll get just cosine squared plus sine squared equals 1, which you know to be true. And that tells you that this does indeed satisfy this equation. And then you can figure out in a couple of different ways that indeed this, if you use the domain of from 0, to 2 pi, then this will also sweep out the entire ellipse. And the reason for that is because one way you can think of this ellipse is you can think that, well, you've got a circle, and how do you take a circle and make an ellipse? You just stretch, the axes, kind of the minor and major axes. You can kind of multiply x by a certain amount and multiply y by a certain amount. And that will actually transform your circle into an ellipse of this form. You translate by A for x and B for y. So that will tell you that you do indeed get this full parametrization. So if you didn't know that, and you're not expected to know that coming into this course, you should know it now. It will be something that will come up again later in the course when we do things like Green's theorem and such like, where we want some parametrizations of ellipses. So I like to include this just for your edification. So parametrize the unit hyperbola. Well, let's ask if we can do it. This has an equation. This looks like the unit square. And I know the very sad fact that I learned the other day is that many of you haven't studied hyperbola. But now I think I inspired you through that lecture to look at these equations. And well, anyway, we know what it looks like, right? So it looks like this kind of, these two, I'm really bad at these drawings, but okay. Looks like these two, we got these two branches. So let's say we want to parametrize this. Can someone tell me if I'm okay? If I can do it? Can I do it? Parametrizations, by the way, they should be at the very least continuous on our domain. They should be continuous. So let's say I wanted my domain to be R. Can I do it? Nobody's bold? Nobody wants to risk it, huh? I see someone nodding. I don't know if that was in reference to boldness or in reference to whether I can do it or not. Huh? I can't? I can't. That's true. I can't do both, right? This is a disconnected space. I can't do that, right? So I can't parametrize two disconnected things continuously with one continuous line. So, okay, how about if I just say, let's just take the positive branch or the right-hand branch. Can I do that? I hope so. In principle, I can, right? You can say, well, in principle, you can start here at 0, and as you go in positive time, you're going to trace this out. As you go in negative time, you'll trace that out. Okay, it seems reasonable. There is such a function. There are a lot of functions, right? The question is how can it be done in practice, not just principle? Any thoughts? Oh my gosh. Huh? Ah, yes. So very good. Actually, that's a good point. So you can actually parametrize, right, by taking a y value, right, and then solving for this equation. This is kind of something you can do. So indeed, you can solve this equation, right? You can say y is equal to the square root of x squared minus 1. Oops, my bad. I did it the wrong way. X is equal to, you want to solve for x in terms of y, 1 plus y squared. This will give you a parametrization. So this is one parametrization. That's a good point. Thank you. Wasn't thinking about it. But let's give you this. So now you just make your variable t here, and then you can take the square root of 1 plus. I think I'm doing something wrong here. I should be taking t in here. That's why. Thank you. 1 plus t squared. T. There we go. All right. So you're solving x for y. So your parameter will just be the y value, and then you can solve for x. This does give you a parametrization. You could also parametrize the unit circle this way if you just took the upper or the right half circles. Right? You could do that. I want to say that this is not my favorite parametrization. There's another parametrization. I thought maybe people would know it, but I don't know. It's not required knowledge. Cosh t, sinh t. These are hyperbolic cosine and hyperbolic sine. Just like the unit circle, if you erase these as parametrized this way, the hyperbolic, you have this. And of course, this, you all know these guys are 1/2 e to the t plus e to the minus t. They also satisfy nice trigonometric, or nice calculus identities as well. Anyway, so this is one parameter. You don't need to know this, but you may need to know it later in your life. So you never know. Okay, so you can put that in a box and put it aside. Now, what is one of the things about multivariable calculus that presents a challenge to us? All right. There's a lot of things. It can get quite complicated as we go up in our dimensions for our domain. But what I want to say is that one of the reasons one variable calculus is so accessible to the masses, right, is because you can draw pictures of the functions or the graphs of functions of one variable very easily. So you see these all the time, people love showing graphs on TV and stuff, and they can see what's going on with a graph. When you go into higher dimensions, right, graphs become a little bit harder to come by, or a little bit more difficult to deal with. So let's just talk about graphs for a moment. What is a graph? So if we have a function f, just look at one variable calculus, and let's just assume the whole domain is R. Then the graph of f is what? It's the pair of points, it's the set of pairs of points, pairs of numbers, I should say, Cartesian coordinates, where you take in, so the pair is xy, where y is equal to f of x. So now let's take a look at this here. So what we have, if I look at the dimension here of the range in the domain, the dimension of this is 1. Okay, sorry, the domain and the codomain. The dimension of this guy is 1, the dimension of this guy is 1. The graph lives naturally in the dimension 2, right? This is the dimension. For our vector valued functions, we're going to go, say, from R to R2. And the graph here, so now we have a dimension 1 here and dimension 2 here. And the graph here, it looks the same. So here we're going to say, I don't know, we'll say t, I guess I'll just say this. Let me do it this way, x, y, and z. And I'll say z is, sorry. What do I want to say here? Maybe let me do it the way I was doing it here. Sorry, my bad, guys. I'm a little tired today. Okay. xy is equal to f. So I'll make a vector here. All right. So this is what we're going to see in a graph of a function from 2 variables is we'll actually see something that lives in 3 dimensions. Now you'll notice here 2 is equal to 1 plus 1, 3 is equal to 1 plus 2. And if I have a function f tilde, or f, a vector valued function from Rn to Rm, then the graph, I'll just say the graph of f is n plus m dimensional. It lives inside, well, I should say it lives in n dimension, n plus n dimension space. So this is one of the things that we have trouble with. And this is one of the reasons we study scalar functions of 2 variables, because we can put them in 3-dimensional spaces, because 2 plus 1 is 3. But once you start getting higher dimensional, it gets very hard to visualize the graph of a function. You have to get higher dimensions, and it's hard to draw those pictures or even have a computer draw. So So however, you can indeed do this in these cases. So you can do these types of functions. These live in 3 dimensions. And you can go, which we'll do later, functions from R2 to R. But right now, let's take a look at an example of a graph of a very well-known and often used vector value function. So let's say I have a function R of t, 2 cosine of t, 2 sine of t. So this will, of course, trace out, if I look at the image of this, this will trace out a circle, right? A circle of radius 2. So, however, if I want the graph of this, so to obtain the graph, I need to go to 3 dimensions. So for that, we'll put in we'll make our coordinate system, but this time I'm going to label my parameter on the x-axis. Instead of x, I'll label it by t here. And then I've got an x and a y here. And maybe what I want to do actually is take my t-axis and kind of look at it both in the positive and the negative part. So now what happens here? So now instead of viewing this as we're parametrizing some static circle of radius 2, what we're doing is we're playing a movie. And we have at a certain point in time, we're given a point. And then time, well, the way I've drawn it, time is going, let's take time going negatively. If we draw it negatively, then we're going to kind of take this and slide this plane, negatively in time and see what happens to our function. And then what will indeed happen in this case is we'll get this kind of thing. It's a really bad drawing, I'm sorry. But hopefully you get the idea. You get this helix. So the graph of this function will be helix. And it just looks like the set t, 2 cosine t, 2 sine t, where t is allowed to be any real number. Of course, this keeps going. Okay, so graphs of functions are something that we often want to be able to do, to work with and to illustrate. So let me look at another example of a graph. So I have the following, so another example. We can look at the function, say r of t is equal to 1 minus t squared. And again, let's say we want to draw the graph of this. Oops. So the idea of how to draw a graph of something like this is to, well, for me, what I would try to do is I'll try to see what sort of the graphs are for each of these scalar functions, and then put them together. This is going to be, it's going to be x, it's going to be y, it's going to be t. So if I just look at the x component, I get t goes to 1 minus t. And I know that if I just think of that as a one variable thing, that gives me the equation for a line of slope -1. And indeed, I can draw that line pretty easily, right? With the help of my here. So there's some line here on the tx plane that is just the graph of this function here. Likewise, I can look at this function in the ty plane and ask, what is the graph of that? T going to t squared. Well, that's a parabola, and I know how to draw a parabola. And so I can hopefully request, I don't know if, does it do it? Yeah, there we go. What a great. So, yikes, I'm back. Okay, so maybe I need to draw this parabola thusly. Come on, it's not very cooperative. All right, okay, so this is a parabola. If it may be a little, the perspective may be a little off, but the idea is this parabola lives in the ty plane, okay? So it lives in this plane here. Now, if I put these two together, I can see what the graph is going to be. Basically, it's the only thing that will project to both of these. It's the only thing that will project to both of these. So if let me draw another, so I can actually kind of draw something. It's not quite a parabola, but should kind of project to it. So it's something like this. It lives over, when I project it downward, it projects to this line. And when I project it to the ty plane, it projects to this parabola. So that will give me the graph of a function. Okay, it's fun. It can be fun if you like to spend your time drawing, taking equations and working them out. It can be kind of fun. And the more important thing is it really gives you, if you have a model or something you're trying to work with, you know, this drawing a graph will give you a real good sense of what, you know, what your minima are and all of these types of things, the behavior of your function. Now, if what we want to do is do calculus eventually, and we do, and we will start doing that next week, we need one ingredient beyond linear algebra to start talking about derivatives and things of that sort. What is the one thing that enters into calculus that you need beyond, you know, functions, lines, and things of that sort? Limits. Good. We need limits. Now, again, when our vector valued functions are of this type, and n is bigger than 1, we are properly in the multivariable calculus setting, and life is hard. Life becomes much harder. This is what separates, for example, partial differential equations from ordinary differential equations, is this n. Ordinary is n equaling 1. That's what you normally study a lot of in, you know, first differential equations class. Partial differential equations is higher, and 2 or greater, it becomes much more complicated. So, but luckily we're only in n equaling 1 case, but in either of these cases, we need a notion of limit. And why are we so lucky? Well, let me give you the definition of limit, and you'll feel, I think, very good about it, I hope. So let's say we have a vector valued function of one variable. And well, then we'll say that limit as t approaches a is a number, of r of t is a vector L, if, and only if, the limit t approaches a of r of t minus L norm is equal to 0. This is a great trick. It's a very great trick. I was able to define limit of a function that lands in higher dimensions by using a function that lands in 1 dimension. If I take the magnitude of a vector of r of t minus L I can think of this whole thing as a single function, which takes as an input t and gives me a real number. And you've taken calculus before, so you know the definition of limit there. So this is a nice little trick. And we can take it legitimately as a definition. If you have never seen the actual definition of limit, who's seen the definition of limit? Okay. I'm seeing people are really like shell shocked here. Like nobody's okay. Really, no one's seen, I mean, really, so who people feel like they know what the definition of limit is? No? Come on, guys, have confidence. All right. Well, there is an actual definition. It's by Cauchy, a really wonderful mathematician, French mathematician. It's a delta epsilon definition. It's not a fraternity or anything. It's an actual delta epsilon. Have anyone heard of delta epsilon definition of limit? All right. So look it up. So I taught when I went to graduate school at University of Chicago, and there they require all undergraduates to take calculus, art majors, everybody's required to take calculus. They also require us to teach delta epsilon. So to art majors and everybody. So it's viewed as a very important lesson in the history of human knowledge. So all of you should go and study that a little bit so that you can be enlightened or something, I don't know. All right. But regardless of that, even if you don't know the strict mathematical definition of limit, we hopefully have a sense as to what it means, and this gives us a rigorous definition for vector valued functions of one variable. But how do we actually use that? Well, for that we have a theorem, and that theorem is really kind of a nice blessing for us, and it tells us how easy life is for one variable functions. So let's suppose we have a vector valued function, and I explicitly write out the components f, g, and h of t. Then the limit as t approaches a of r of t exists and equals, say, BCD, if and only if the limit t approaching a. Okay, so now this is where notability is like just a lovely thing. It's like 3 times the pleasure, right? There we go. If and only if each of the components have these respective limits. So you can test for a limit of a vector valued function just by looking at the components and taking the ordinary one variable limit. Nothing new, nothing difficult. Okay. Again, I want to really emphasize, this is not the case. This is not as easy when we have 2 variables as our inputs or more. It is not as easy. That can become much more complicated. And we'll see that in a bit. There are also then, using one variable calculus, there are a bunch of rules that we have at our fingertips now with this theorem. Again, I won't prove this theorem, so I won't subject you to such torture. But indeed, we should know that there's basic arithmetic rules. They all apply. Namely, if I take the sum of two vector valued functions and take a limit, the limit of the sum is the sum of the limits, assuming all limits exist, right? Difference of the sum, limit of the difference is the difference of the limit. There's also the thing like the limit of the dot product, which is a scalar valued function. Say I take two vector valued functions. So maybe, for example, e.g., if I take the limit as t approaches a, and I have two vector valued functions, this will indeed equal the dot product of the limits, which are two vectors. Assuming, again, assuming everything exists. We always have to assume these limits exist. There is there's a problem in the practice exam that I don't know if it uses exactly this, but you should think about things like this to maybe understand some things. Okay, so let's do a problem, and then we'll see how good we feel. So let's find the limit, if it exists. Take the limit as t approaches 0, and I'll go from the right. So you, of course, can, all of these definitions, you just go from the, if I'm saying, a limit from the right or from the left, you can put that into all of the definitions and all of these properties as well. Of the following vector valued function. I'll just write it out. Okay. Okay, so let's see if we can't get a solution. Okay. What do people think? So what you're going to evaluate here is you're going to evaluate each of these components. So let's look at the first one. How do people feel? How do people feel? Any ideas? -1. -1 is an idea. This is one variable calc. I mean, this is pre-calc, I think, one variable pre-calc, right? Indeed, if you're faced and confronted with a rational number, or a rational function, excuse me, so a quotient of two polynomials, then you have to just check one thing to evaluate the limit, namely, is it indeterminate? Is the denominator going to 0 or not? As t approaches 0, the denominator approaches -1, which means this function is going to be continuous at that point, 0. So here you just have to put in the value. So you just get 1 over -1 or -1. Good? Very good. So let's look at the y component. Okay. Who has the Solution, yeah, yes. All right, good, very good. 1. Why? An exception. Uh-huh, okay. So it was something you recognized from, okay, that's fair. Can anyone give me another rationale for why this is 1? Yeah. Okay, so this is an indeterminate form. What we do with indeterminate forms, we remember good old L'Hopital, a scoundrel. Everyone knows that, right? Yes, should be called Bernoulli's rule, but he paid Bernoulli to give him a theorem. It's horrible. Anyway, but he's in history, so L'Hopital, right? Okay, so L'Hopital's rule does apply. Take the derivative of sine over the derivative of t, get 1. However, that's excessive. Is there another reason? More foundational. More foundational, even than that. I'm just going to start bringing back good memories. More foundational. Yeah? I really couldn't hear you still. Close. Derivative of sine. This is actually the derivative of sine. Right? How do you define, I just want to go down memory lane, guys, since I have you all here, and since it's a calculus course. All right. What's the definition of the derivative of a function of one variable? It's this, right? Everyone knows this. So do that for sine at 0. Right? Sine of t plus 0 is sine of t. Sine of 0 is 0. This is the definition of the derivative of sine. I mean, sure, I'm just going from the right, but okay. Yeah, you can. So you don't even need L'Hopital. I mean, this is just the definition of the derivative of this function at 0. And I think the young woman said that she recognized this limit. This limit. And this is probably where it was recognized from, because it does appear. This case is how you get that the derivative of sine is cosine in most calculus books. You work out this case. All right, so last one. T to the 2t. Okay, guys. It's time to show your stuff. Right? Huh? Log? Okay, so let's take a look. Limit. So what is t to the 2t? I think someone's saying to use a log. I think that's correct. I can do that. E is continuous. So this reduces to the question of finding the limit of the exponent. So what is the limit as t approaches 0 plus of 2t ln t? Well, so as t goes to 0, this goes to 0. As t goes to 0, t goes to 0. But ln t goes where? Negative infinity. So I may agree or may not, let's see. But before I get there, I would need a justification of why it might be what was suggested here. So for that, I will just recall, or just do a little arithmetic. I'll bring the 2 out here. And I'll write it this way. And now I have a nice true indeterminate form. I don't have a zero infinity. I have something going to negative infinity over something going to infinity. That's a nice, now I can apply L'Hopital and take the derivatives. 1 over t, negative 1 over t squared, which equals 2 limit. I guess I'll bring the negative sign out of t. And yes, indeed, it is 0. It's going to 0. So since this exponent goes to 0, this limit goes to e to the 0, because e is continuous, which is 1. How do people feel? Do they feel good? Do you feel refreshed? Do you feel like this is all coming back now? All right, let me get in one more definition, guys, before we break for the day. Okay, just one more definition. We want to be able to consider certain types of vector valued functions. We're going to talk, a very difficult notion is the notion of differentiability of a function, of a vector valued function of many variables. One variable, not so much. However, a more fundamental or easy notion is continuity. And so, and the definition is the same as in the one variable case, but I do want it in the notes. So we say a vector valued function R of t is continuous at A if when we take the limit, and this would have to be the two-sided limit if A is in the interior of our interval, or the one-sided limit if it's, say, an endpoint of R of t is indeed equal to R of A. It's the same definition in one variable calc, but it is something we want to understand. If it's continuous at all the points in its domain, it's a continuous vector value function. All right, guys, I'll see you on Tuesday.